Hello friends. Friends, today we will discuss the second boundary condition for electromagnetics, that is H tan 1 equals to S tan 2, and for perfect conductor S tan 2 minus S tan 1 equals to current density Js. Okay, or it may be S tan 1 minus S tan 2 equals to Js. So let us start with a statement. The tangential component, the statement is the tangential component of magnetic field H is continuous across a surface except at a surface of a perfect conductor. Okay, if there is a boundary and along this axis, along this side there is a component H11, along this side there is component H2. Okay, then if these components are equal and parallel, okay, parallel components are known as the tangential components. I have discussed in my previous video lecture of the first boundary condition related to electric field. I will share in the description box. So H tan 1 equals to H tan 2, continuous, they are continuous, equal. But at the surface of a perfect conductor, they are not equal, they are not continuous. Then H tan 2 minus H tan 1 equals to Js, or H tan 1 minus S tan 1 minus S tan 2 equals to Js. Okay, if we take the magnitude only. Okay, now to understand this, let us have a rectangular loop. Okay, I will again redraw here. Let us have a rectangular loop. Okay, having, this is the surface of discontinuity x equals to 0, and this loop is having width delta x, okay, and having length delta y. Okay, now A, B, C, D, E, F. This is medium 1, this is medium 2, medium 2 having characteristics epsilon 2, mu 2, sigma 2. This is having characteristics epsilon 1, mu 1, sigma 1. Okay, now from A to B, the component is Hx1. Along this rectangular loop, the current is passing. Due to current, magnetic field will be there. Hx2. Similarly, from F to E, Hx3. From E to D, Hx4. Okay, you may refer this diagram also. Okay. Similarly, from EY2, and this side is HY2, and here it is HY1. Now apply the Ampere's circular law. That is the closed line integral of the magnetic field H is equals to the current passing through the circuit. Ampere's circular law. Okay, we can derive this boundary condition with the help of Maxwell equation also. I will tell you later. So expand this. Now from A to B, Hx1 dl, from B to C, Hx2 dl, from C to D, Hy2 dl, from D to E, Hx4 dl, from E to F, Hx3 dl, from F to A, Hy1 dl, and this is I. Okay, now Hx1 dl. Now we will solve dl. Now what is dl from A to B? Delta x by 2. What is dl from B to C? Delta x by 2. What is dl from C to D? Delta y, but with a minus sign. Now why there is a minus sign? We are assuming here that from F to E, it is a positive direction. Then from C to D, if I am moving from C to D, then it will be a negative direction. So for the minus sign is due to the path dl. So that's why there is minus sign. Similarly, from A to B, it is a positive x-axis. From D to F, it will be minus x-axis. So that's why here it is minus Hx4 delta x by 2, minus Hx3 delta x by 2. Then plus Hy1 delta y equals to I. Okay, now if delta x tends to 0, then this will become 0. All delta x terms will become 0. This will become 0. This will become 0. And this will become 0. We will left with Hy1 delta y minus Hy2 delta y is equals to I. Okay, or take out common delta y equals to I, or Hy1 minus Hy2 is equals to I divided by delta y. Now current per unit length is known as current density Js. Okay, or hy1 minus hy2 is equal to Js. Now these hy components, this component and this component, they are parallel. They are the tangential components. So h tan 1 minus h tan 2 is equal to Js. Okay, this is for the perfect conductor where there is a current. Okay, now if there is no current, then q is equals, if there is no charge, then I will be 0, then j will be 0, current density will be 0, so right side will become 0. So h tan 1 minus h tan 2 is equals to 0, or h tan 1 equals to h tan 2. Okay, this is the statement, that is the tangential component is continuous except at the surface of a perfect conductor. So the second boundary condition has two statements, that is the magnetic field is continuous, this statement, across the surface of discontinuity, except second statement, at the surface of a perfect conductor. Now this we can solve with the help of Maxwell's fourth equation also. Now what is Maxwell's fourth equation? That is H dot dl. Okay, this is the second method if you want to do. H dot dl equals to integral of j dot ds plus jd dot ds. Now j dot ds is conduction current, j dot ds is conduction current, jd dot ds is displacement current, and total will be current. So again h dot dl equals to I. So we will reach here again, but here current is only the conduction current. Here the current is conduction current plus displacement current. Okay, then step will be same. Okay, so you can use any one of the methods. Okay, while solving this boundary condition, that's a very useful to solve the various electromagnetic problems. Okay, so I hope you have understood. If there is any doubt, please share in the comment section. Thank you. Thanks a lot.